Okay, so we have just been talking about photoreceptors and rods, and you may remember I was talking about how we have these opsins in our eye that are proteins, and that we have some for our rods, and we call them rhodopsin, right, or rhodopsin. Our rods are going to be very sensitive to light. They're so sensitive, in fact, that light and just too much light can disrupt these cells completely. And the way they do that is too much light will basically disassemble the protein. In other words, whenever you see a lot of light, what your rods do is they temporarily break down. The protein that powers that cell temporarily breaks down and will wait until there's less light to recombine itself to function. So this is part of the reason why whenever it's night, if someone shines light in your eye, it kind of hurts, right? But part of what's going on is that all the protein that's powering your night vision has been disassembled, has been deconstructed. And so as soon as that flashlight is out of your face, it's still really dark, but your night vision doesn't come back, right? Your night vision doesn't come back immediately, and that's because of it takes several minutes for this rhodopsin to recombine itself, to work, to repower that cell again. And that is just the how long it takes for us to go from day vision to night vision, which is, depending on the person, about 20 minutes, 30 minutes or so. So whenever this is going on, our pupils at night are going to dilate, so they're going to, the iris is going to make the pupil bigger so we can let in more light so that we can kind of see things a little bit better. But whenever the lights are bright, what happens is our pupils do this. They get really, really small, so they let in less light whenever there's lots of illumination. So one of the things that can happen with certain problems that we can have in our retina, specifically in the rods, is retinitis pigmentosa. And so retinitis pigmentosa is going to be a kind of disease-based condition that affects peripheral vision and works its way inwards. And so usually what happens is that people that have retinitis pigmentosa will start losing out on their peripheral vision, and then it gets worse and it gets worse and it gets worse until they're left with just these tiny little dots for their visual field. And so this is something that happens over the course of about 10 years or so. There's a video on here where you can kind of see what it would kind of be like to live like that. If you want to check that out for a visual example. But this is something that, unlike macular degeneration, is something that it seems like people are able to get prostheses for. So you can actually get a prosthetic retina to help see that. And we're going to look at what that might entail in later chapters when we start talking about retinal implants and being able to see using cameras and things like that. So, on the way to, and this is a figure that you're going to see in your textbook, but don't worry too much about it. It's very technical, and I'm not going to ask that you know all this stuff about bipolar cells, horizontal cells, and amacrine cells. You're not going to need any of that material whenever you leave this class, and so I'm not going to make you learn it. But here's what's important about this figure, is that what you're looking at here is kind of the opposite of what you would expect. So in this, and this is what it actually looks. This isn't a drawing. This is what it actually looks like. So you can kind of see these different photoreceptors up here, right? So we have light that is coming in, and it hits the back of your eye. So the light is going to pass through all the colors that you see, all the details that you see. Are going to pass through all these cells to hit the very back of your eye, which is where these photoreceptors are. From there, those photoreceptors are going to become active, and they're going to send the signal back forward to the front. We're still in the retina. But we're moving forward just a little bit so that we're going through these different cells. And what we're ultimately going to end up with are these ganglion cells. From the ganglion cells, then we are going to move to the optic nerve, which is going to take that over to different parts of the brain for later processing. So what you need to know about this figure is that light is going to move all the way to the very back of the eye and then move forward a little bit before being transported to the optic nerve. So whenever we talk about details and we talk about visual acuity, we measure that using what's called a visual angle. And this is something we're going to talk again about in Chapter 3. But a visual angle is basically just how large something is to your eye. So, and I know it can be very tempting for somebody to say that, like, oh, that is 3 inches long or something like that. And so if you're doing another study to compare with somebody, you would just say, oh, just get a stimulus that's 3 inches long and it's the same. But it's not. So if I, just for example, let's say that I was going to compare my vision with my dog's vision. So if I were going to do that, one of the things that I want to do is control for how big things appear in my visual field. I would want to make sure that if the phone is this big to me, and I'm trying to in my study is like looking at how much detail I can pick up off my phone, and I'm going to compare that with my dog, I wouldn't necessarily be able to show my dog, the exact same phone. Right? Because our eyes are different shapes and it's different sizes, and so this phone may be much bigger to his eye than it is to my eye. And also we have to take into account how close it is to our eye. So that relative size is the visual angle. How big is that detail, is that object on the rest of your eye? So that way you can compare with you versus somebody else versus your dog or another species or with different age groups, things like that. And so whenever scientists talk about this, usually you're not going to see them talk about like a 3-inch object or a 4-inch object or whatever. They're going to be talking about 45 visual angles or 20 visual angles because that's a little bit more informative for scientists. How big is one visual angle? If you were to basically give me a thumbs up right here, you have your thumb out at arm's length. The width of your thumbnail, as long as it's not in your blind spot, is going to be roughly about 2 degrees. So that's about 2 degrees of visual angle. And that is where the phrase rule of thumb comes from. It's not the urban legend about the old Puritan or Victorian law in Britain about the width of a stick. If you don't know about that, you can Google it. It's a whole other thing. But that's where the phrase rule of thumb comes from. Okay, so very briefly, we're going to talk about receptive fields, and I'm going to start this conversation now. We're going to talk more about it in the next chapter because this is going to be a really big, important thing that everybody gets wrong on the exam. Not everybody, but this is a very common, very tricky thing, so I want to spend some more time with it. The ganglion cells in our retina, they are sensitive to where light is occurring. So those cells are going to be telling us where light is, which is really important. And so they do this by having 2 different flavors of cells. An on-center cell, sometimes called an on-off. I will call them an on-off cell, and an off-center cell or an off-on cell. The on-center cell, this is whenever you have in the middle of that cell, if there's light falling on that part of the cell, it is going to increase that neuron firing. But if it is on the outside part, then it is going to slow down. So I'm going to show you an example right here. This is an on-off cell or an on-center cell. Oops, sorry. So what you're looking at right here. And so if this yellow spot is light and is right here just in the middle, this is going to be an excitatory center. So it's going to be the part of the cell that is excited and it's going to start firing more frequently. And so if we were looking at that in terms of measuring using single cell recording, how quickly is it firing, this is what we're going to see. We're going to see almost baseline levels, nothing new, nothing unusual. But once that light hits, then we have many of these action potentials. And so, again, it's not how strong a signal it is, but it's how frequently it fires. And so what you're seeing here is dot, 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 right? Because that light is now on that center part of the cell. If we take that same amount of light and we shift its direction so that it's now over the surrounding part of the cell, this gray spot, it's not actually gray, but just for the visual it is. This is an inhibitory surrounding area. And what happens is that it's going to create an inhibitory response and stop firing. And so, I will say this so many times this semester because it's really important. Again, it's not how strong the signal is. Instead, it's how it changes the frequency of the action potentials. Does it fire more frequently? Does it fire less frequently? Or does it fire the same? Those are the three things that our brain understands. Is it more frequent, less frequent, or the same? So what we're seeing here is that it's less frequent whenever light hits the surrounding part of the cell. If we were to look at the other category of ganglion cells, what we see is just the opposite. So for the off-center ganglion cell, the excitatory part is now in the surrounding area where the inhibitory part is right here in the center, so it's the exact inverse, where you have light hitting the center and it basically shuts off the cell. Whenever you have light in the surrounding part, then it becomes very excited and starts firing more frequently. Okay, so you may ask, Dr. Daniel, what would happen if you illuminated the entire cell? What do you think would happen? If you said it would cancel it out, you are absolutely right. Why? Because if you were to take this light and you were to move it across the entire cell, what happens is that it's going to hit it's going to hit the inhibitory part, but it's also going to hit the excitatory part, and they are going to cancel out, which means that it's not going to be excitatory or inhibitory. And this is what we're seeing right here. So what we're looking at right here is an on-off cell. In this on-off cell, or this on-center cell, you have initially a little bit faster frequencies, because firing a little bit faster. As we increase it, so the light is taking up the entire center, then it's firing even more frequently. We expand it a little bit, so now that it's hitting some of the inhibitory parts, and we see that that is slowing down, and then if you cover the entire thing, then it just goes back to baseline. So what are these things used for? We'll talk more about that in Chapter 3 when we start talking about lateral inhibition and feature detection. I'll see you there. Bye.